Hello everyone, welcome back to the second part of this video series on final exam review. We are going to now see a problem on extended surfaces or fins. Now here is a problem. There is a plate. This plate has small extended surfaces which are pink in color, right? There are many fins placed on this plate. Now we all know that the role of this fins is to remove heat from the surface, right? So the problem says that the hot surface at 100 degrees is to be cooled by attaching 3 centimeter long 0.25 centimeter diameter aluminum pin fins with thermal conductivity 237 watts per meter Kelvin. So this is the length of the fin, that's 3 centimeters. The distance between two fins, center to center, is 0.6. The diameter of the fin is 0.25 centimeters. Right? Center to center distance is 0.6. The temperature surrounding air is 30 degrees, that's T infinity. The heat transfer coefficient on the surface is 35 watts per meter square Kelvin. Assume the heat transfer from the fin tip is negligible. This is an important point. What does it mean? So, more or less, this fin tip is sort of adiabatic in nature. Because the heat transfer is negligible. You cannot add heat, you cannot remove heat, so we can consider the fin tip to be adiabatic in nature. This is important because we need to identify the cases from the table. The formula sheet is given to you. So you have the formula sheet, and from there you need to pick the appropriate formula depending upon the case. Now we need to determine the rate of heat transfer Q from the surface for 1 by 1 section of pipe. So 1 meter by 1 meter section of plate. And we need to also find the overall effectiveness of the fin. Let's start the problem. Let's write the given data. So the given data, what is given to us? Let's sort it out. So the base temperature is 100 degrees centigrade. The surrounding temperature, T infinity, is 30. Diameter of the pin is 0.25 centimeter or 0.0025 meter. Length of the fin is 3 centimeter or 0.03 meter. Heat transfer coefficient is 35 watts per meter square Kelvin. K is 237 watts per meter Kelvin. Conduction. This is convection, this is conduction, right? We can calculate the area of the fin. It's pi by 4 d square. So pi by 4, we know the d, it's 0.0025 square. So we'll arrive at 4.91 into 10 power minus 6 meter square. We can also calculate the perimeter of the fin, that is pi times d. So 3.14 times the diameter 0.0025, that is 7.854 into 10 power minus 3 meter. So this in summary is the given data. Now from this data we need to find the efficiency of the fin, the Q, and the overall effectiveness of the fin. Now one of the important factors that before you start any of your calculation, like in this case, step 1, we need to calculate M. M is equal to root of H times P divided by K times the area. So H times the perimeter, divided by K times the area. So if you substitute all your values from above, so we have 35 times the perimeter, that is 7.854 times 10 to the power minus 3 divided by K is 237 times the area, 4.91 times 10 to the power minus 6. If you solve all this, you should get something like 15.37 per meter. That's the value of L. M. Then step 2, we are calculating the product of M times L, that is 15.37 times 0.03. We get something about 0.4611. Then we are going to calculate the efficiency of the fin. So the efficiency of the fin is tan of tan h, that's the hyperbolic function, m times L divided by m times L. Now remember, this is in the case when the fin tip is insulated. Now this formula is available in the table in the formula sheet. So that's tan h hyperbolic function times ml is 0.4611 divided by 0.4611. So we get the efficiency of the fin at about 93.47%. That's the efficiency of the fin when the fin tip is insulated. The next set of steps contain how we can determine the overall efficiency of the fin. Now remember that it's a plate, right? It's a plate. We only know the dimensions of the fin. We are not sure how much is the length of this plate and how much is the height of this plate and how much is the thickness of this plate. Those details are not given to us. But nevertheless, we are going to assume the dimensions given to us about the fin, and we are going to calculate how many fins are available on this plate, because more number of fins, it means that the efficiency will go up, the rate of heat transfer will go up. Less number of fins means the efficiency will be less and the heat transfer will also be less. So next step number 4, we are going to calculate the number of fins. That's N. That's not efficiency, N. That is the total area of plate divided by the fin spacing square. Now in the question he says that we need to take the area as 1 by 1. So the area of the plate is 1 square meter. The area of the fin we have calculated, it's 0.006 square meters. If you divide, approximately the total number of fins are 27778. So we have 27,778 fins over the plate over an area of 1 square meter. That's the meaning of this step. So we know the number of fins, so we can easily know how much amount of heat is being transferred to the surrounding air. Right. Now let's calculate the fin area, the total fin area. Right. that is number of fins, that's n, times the surface area of this fin, surface area of fin, plus the cross-sectional area of the fin, right? Because heat is getting transferred from the surface as well as the cross-sectional area of the fin. Okay. So let's calculate this. So n we know it is 27,778 times surface area of this of the fin, pi, times the diameter, that's 0.0025, times the length, that is 0.003, plus cross-sectional area, pi into diameter square by 4, so 0.0025 square divided by 4, so square is here. If you plug in all the numbers, you are going to get the total fin area of 6.68 meters square. That's the area occupied by the fin, right? So that's effectively where the heat transfer increases in the plate, right? Because to accommodate 27,778 fins, we need an area of more than 6.68 meters square actually. Now we need to calculate step number 6, total unfinned area where no fins are present, because the heat transfer will be less in this area. So total unfinned area is equal to the total area of the plate minus the total finned area. Finned area. Remember that this is area, right? So pi d square by 4. So total area of the plate, we are considering it as 1 as given in the question, minus number of fins 27778 times area of one fin is pi, that is 3.14, times the diameter square 0.0025 square divided by 4. So you plug in all the numbers, the total unfin area comes to 0.86365 square meters. So out of 1 square meter, 0.8635 is unfinned area. Now let's calculate the efficiency. Efficiency is equal to heat transferred by the fin area divided by maximum heat transfer from the fin area. Now I know the efficiency because I have calculated it before, 93.47%, right? In step number 3, you see the efficiency is calculated here, right? So I know the efficiency, but what I don't know here is how much amount of heat is getting dissipated from this fin area. So efficiency is 93.47% is equal to Q fin, I don't know, Q fin max. How do I calculate the heat? It is convection. So H times area of the fin times delta T. Q fin is equal to efficiency, that is 93.47 divided by 100, times H is given to me, it is known to me, it's 35. Area I have calculated 6.68. Delta T is 100, that's the plate temperature minus the room temperature 30. So if I do this, the fins are dissipating a heat of 15,300 watts or 15.3 kilowatts. Right? That's the answer for the fin heat transfer. But you see, there is certain area which is also unfinned, and we need to calculate the overall efficiency. So step 8, we are going to calculate the unfinned heat, that is area without the fins. So that is H times area without the fin, that's unfinned, times delta T. Now area without the fins I have calculated. It's here 0.863. H I know, so that is 35.0 times 0.86 times 100 minus 30. So the unfinned area is giving out 2107 watts. Right. So if you look at the plate, there are gaps in between the plate, right? These are unfinned areas, these are finned areas. So these gaps are giving 2107 watts, and these fins are transferring 15,300 watts. See the difference? The unfinned area and the finned area. That's why fins are important. Now step 8, how much amount of heat is getting dissipated? We need to add both the fin area plus the heat from unfin. So that is 15,300 plus 2107. So the total is 17407 watts. Right? That's the total amount of heat that is getting dissipated. Now, if I say that 1 square meter area has no fins, then how much amount of heat is getting transferred? So let's calculate that. Q is H times area times delta T. So H is known to me, 35, area is 1, delta T is 100 minus 30. So we are getting without any fin, I can transfer only 2450 watts, but with fin, look, see the difference, I can transfer 17,407 watts of heat. So overall efficiency, if I have fins, how much is the heat transfer? If I don't have fins, how much is the heat transfer? So with fin, I'm transferring 17,407. Without fins, 2,450. If you divide, it is somewhere about 7.1 times 100. That is about 710%, 710%. So that much amount of energy can be, that much amount of heat energy can be transferred. You see the difference? When there is no fin, I am transferring any 2,450 watts, which is nothing. And when I have fins, I am transferring 15,300 plus the surface is also transferring some amount of energy because there are gaps between the fins, and the total is way far when compared to no fins. And that's how I'm increasing or improving the efficiency of heat transfer. I hope that's clear. Thank you.